Hello, today we will be doing homework for part A. First, we are going to start out by looking at the damping in a manometer in terms of pressure drop associated with the laminar flow. We are going to look at the transfer function that relates the height difference between the fluid levels in a manometer to the pressure differential. So we can start off by drawing our manometer, and we will have two different liquid levels in here, and we'll define the difference in these liquid levels as H. And we can also start out by writing a force balance, and just in general, we know the forces that we'll have are obviously gravity, the force of gravity on our liquid. There will be the force of the atmospheric pressure. And then there will also be force of the viscous pressure. And so if we want to write this in numerical terms, first, we have to define which direction we want to be positive. So I'm going to say moving downward is going to be positive. And our gravity is going to be negative g rho a h, a being the cross-sectional area of the manometer, and then h being that height difference for the liquid levels. And our atmospheric pressure is just going to be P times A. And then for our viscous pressure, that's going to be a term that we will solve for down here. So that will be blank, but we can start out by writing the change in pressure over the density equals 4FL over D, then V average squared over 2. And so F here, color. So F is, according to the problem statement, 16 over our Reynolds number. And so this is our fanning friction factor. I'm saying that correct. So if we kind of rewrite this equation, we end up getting 32 L, and then we'll get our V average squared, and then times our viscosity over D times our density times our velocity, and then times our density again. So we can see there are a few things we can cancel out here to make this a little simpler. Again, this equals delta P over rho. And so we see that this V cancels out. We can combine our D's, and then this rho will cancel out. I think that's it. So we can rewrite again. Our change in pressure equals 32L times V average times our viscosity over D squared. Now we will multiply both sides by our area, and end up getting, we'll get the rho viscosity times our A to be equal to 8 pi times our viscosity times our change in height with respect to time. And so this right here is actually what we will end up plugging in up here. So I will rewrite our force equation our first balance. So again, our gravity term, G rho times that cross-sectional area times the height, plus our pressure times our area for our atmospheric pressure, and then plus our viscous force equation down here that we just came up with. And so to look at this further and take a second derivative, we have rho A H times d 2h over dt, and then that will equal this whole side of the equation. And then we will rearrange it because we want to take a Laplace transform and we want to be able to see our transfer function. So we're going to end up dividing everything by this rho AH term, and if we rearrange this, we will get our second derivative term here, plus, and then our gravity term here, since we're dividing it by the PAH, we will end up getting just G over L. And then we will get 8 pi times our viscosity divided by rho AH, and then times our change in height with respect to time. And that is going to equal 1 over rho L times our pressure there. So I'm going to just swap these two terms so that it's easier to see. Oops, just rewrote it. Okay, so we'll move that in the middle so it's easier to see our next step here. And so we can define some of these terms just so that it's easier for us to eventually code, and just so it's easier so we don't have to rewrite everything. So we will define this here as our beta. This will be our gamma, and this will be our alpha. So when we take the Laplace transform, so take the Laplace transform of this equation that we have, we will end up getting s squared h plus beta s h, and then plus gamma h. And that will equal alpha p. Oops. So if we rearrange this to get h by itself, you will get h equals alpha over s squared plus beta s plus gamma, and then that will all be times our pressure. So what we have here is our transfer function. And this is relating the pressure and the forces of the pressure to our change in height of the liquid level up here. Now we will look at an example of this in Colab. All right, so I went ahead and put in our variables from our problem statement right here. And we can go ahead, we need to define our area. Our area is, it'll be pi times our diameter squared, oops, all over 4. And then we need to define our alpha, beta, and gamma, which we have here on my iPad. So our alpha was equal to 1 over rho times, oops, times L. And then we have beta equals, had 8 times pi times mu times, or no, divided by rho times our area. Then we have our gamma, which is equal to just gravity divided by our length. And then we need to define our transfer function, k, which that is equal to just our alpha over our gamma. And then our tau, our time constant, is equal to 1 divided by the square root of gamma. I believe that's it. And then we also have our zeta, and that is our beta divided by 2 times the square root of gamma. Okay. And then we can return our k, tau, and zeta just to make sure that they're correct. Okay. I'll get that. And then now we need to define our GP. So our GP will be K divided by tau squared times S squared plus 2 times zeta times tau times S, and then plus 1. Okay. And then we want to do TH equals sim. We want to sim GP. We want our lambda T to be 5E3 because we want to simulate the response of the system to a 5,000 PA step change in pressure. And then we want N to equal 1,000 and dt to equal 0.1. And then we can go ahead and make our plots. So fig equals make underscore subplots fig dot add, oops, scatter x equals t, y equals h, and then I think that's all we need for now. Okay, so as we can see, when it first starts out, there's a lot of oscillations here, and then our system does end up going to a steady state at about 0.51. So now we can go back to the iPad and do part 3, which is to look at 2 first order systems in series and show that they will always have a damping coefficient that's greater than 1, so therefore it would be overdamped. So we can move back to my iPad. So now we are going to look at two first order systems in series, and we know that this general format is k over tau s plus 1. So if we had two, we can say tau 1 and k1, and then we'll have k2 over tau 2, 2s plus 1. And we have our GP up here. So now if we were to combine this into one GP, we would get K1, K2 over tau 1, tau 2 s squared plus, and then it would be tau 1 plus tau 2 s, and then plus 1. So if we compare this to our GP from up here, we can see that tau 1, tau 2 is tau 2 according to our transfer function. So this is tau 2. And this is our 2 zeta tau. And so if you recall, our overall tau is equal to the square root of tau 1, tau 2. So therefore, tau 1 plus tau 2 has to equal 2 zeta tau. So we can simplify this. Tau 1 plus tau 2 over 2, this squared has to be greater or equal to the square root of tau 1, tau 2, also squared. And if we expand this, get tau 1 squared plus tau 1, tau 2 plus tau 2 squared over 4 is equal, or not equal, has to be greater than or equal to 4 tau 1, tau 2. And sorry, there is a 2 here as well. But if we rearrange this more, you can get tau 1 squared, and then it'll be minus 2 tau 1, tau 2. And then plus tau 2 squared has to be greater than or equal to 0. So our tau 1 minus tau 2 squared must be greater than or equal to 0. Therefore, first order systems are always overdamped. So now we can go ahead and simulate this in Colab. So we will be doing part 4 now. We will simulate the behavior of a second order system using different damping coefficients. So we can start with k equals 1, which is our alpha over gamma, and then we can define tau. Equals to 1, which is 1 over square root gamma. Sorry, 2 times square root gamma. And then we're going to define our natural frequency as Wn, which will be 1 over tau. So this is our natural frequency. And then we need to define our GP. Sorry, I mixed this up. I forgot to put in our zeta there. our zeta will equal 0.2, and that is going to be beta over 2 times square root gamma. And then our GP will be the same thing that we used over here. So I'm just going to copy and paste that. And we want to simulate this. So TH equals sim GP. And then lambda T, we want that to be pi dot sine of WN times T. And then we want N to equal 1000 and dt to equal 0.1 again. And then do fig equals make subplots. Fig dot add scatter. We want x equals t, y equals h, mode lines. All right. So as we can see here, there are a lot of oscillations that are pretty close together. And so what we will see, this is the natural frequency here. If we put a multiplier in front of what is inside our sine term, if we put something in there, let's say 0.2, we'll see that it actually widens out. The frequencies become less frequent and they spread out. So we could even do 0.4 as well. See, that's a little higher, so it'll still be a little closer together. And then as we get closer and closer to 1, it gets closer to as if there's no multiplier at all. So this plot shows the behavior of a second order system with those two different damping coefficients.